Hey, Alice Miss Johnson. Back at it again with some calculus. Today we learned that the derivatives of sine and cosine are cosine and negative sine, which is pretty nice. So we're going to practice taking some derivatives with our fun facts that we know, which is the power rule and the two things that I just listed, and plus all the derivative rules we know about pulling out constants and adding derivatives and stuff. And then we're also going to do another optimization problem just so we can kind of nail down that thinking. Let's see how it goes. I'll do examples, and then the questions on your work today are similar, but you'll get a chance to practice them by yourself. All right, let's dive in. First off, I think when you're doing this problem, you should have your note sheet right next to you, right? So on that note sheet, you'll notice that the derivative of sine is cosine, and the derivative of cosine, I should have kept the skinny pen, is negative sine, right? That should be next to you when you're doing your problem. I'll put it next to me when I'm doing my problems. Here we are. So we take the following derivatives. This symbol means take the derivative of this. So we'll go ahead and take that derivative. The derivative of 3 times x to the 7th is 21 x to the 6th, because we multiply the 3 and the 7 and knock down the exponent. It's the power rule. And then the derivative of sine is cosine, so the derivative of negative sine is negative cosine. The reason we do that is we say this derivative is cosine, and we keep the coefficient. That's a done problem. Nice. Next, if we have 13 times cosine plus 9x squared plus sine, we do 13 times the derivative of cosine plus 18x. Doing 9 times 2 is 18. Knocking the exponent down is just 1. And then the derivative of sine is simply cosine, nothing fancy. I'm then going to rewrite this as negative 13 sine. Instead of 13 times negative sine, it just looks nicer. And then all of this is already in its simple, nice form, so I'll just rewrite it. That's going to be the answer I submit. Box this one too for consistency. And finally, for our examples, we've got what's the derivative of 4 times sine x minus 5 times cosine x. We've got coefficients, so we'll do 4 times the derivative of sine minus 5 times the derivative of cosine. Simplifying that, we get 4 cosine plus 5 sine. The negative times a negative cancels and becomes plus. We could go straight from here to here. I don't need to see this work. I don't need to see this. I don't need to see this to count for full credit. I just want to let you know kind of what's going on behind the scenes. All right. Make sure you're careful. Be careful with your signs, right? That's the thing people mess up the most of all when they're doing derivatives of sine and cosine. Optimization. So let's move on to an optimization problem. I know we've done these before, but hopefully continuing to do them, continuing to practice, they'll click one day and we'll all be confident. All right, so here's a function that describes how many dollars this YouTube account is worth, like and subscribe, whatever, per day, where X is the days since school started and Y is US dollars. This is not based on reality, obviously. Find the local maximum and minimum values, X and Y coordinates. Okay, so I want to know when was my YouTube channel worth the most and when was it worth the least? But like in a local sense, not in a global sense. The plan there, let me actually mute this chat really quick. Oh, I see, that's fine. The plan is we have an equation. We're going to take that equation's derivative because we want to maximize or minimize this equation. So we take its derivative, we set it equal to 0, and then we solve, right? That's the plan for once we have an equation, how to optimize it. Okay, well, we've got the equation. Let's take the derivative. We do the power rule here, power rule here. Technically, these are also the power rule, but on your notes, we called this derivative of a linear term, and this was derivative of a constant term. But either way, we find the derivative. I'm going to not put plus 0 because it's extra lanyet. I'm going to set this equal to 0. And now I'm going to solve. I'm going to solve. I might have a different instinct than y'all do on this. I like the quadratic equation. I think it's fast. I think it always works. So I'm a big fan. Ooh, let's make this plus 22, so this actually works. 22, boom, boom, all over 2 times a. So to solve this, we either need to factor or use the quadratic equation. And this will be the same for your example. So I'm going to use the quadratic equation. It's already set equal to 0, so we're good. I am going to plug this into a calculator. I should have done this beforehand, but here we are. Plus the square root of 4 squared minus 4 times a times c, all divided by 2 times -3. I always check what I plugged in is right because I don't like typing it twice. Okay. X is either -2.12 or $3.45. I'm done, psych. Gotta make sure that we're answering the question that they're asking. Find the local maximum and minimum values x coordinates and y coordinates. We haven't done the y coordinates yet. So we say when our x coordinate is -2.12, what's our y? And when our x coordinate is 3.45, what's our y? How would we find this? Do we plug it into the derivative? Do we plug it into the quadratic equation? Do we plug it into the original equation? There's all this stuff going on. It's the original equation, right? When we want to know y, we plug it into here. If we wanted to know y prime, or if we wanted to know the slope, we would plug it in here. But when we want to know y, we just find the equation that says y and we plug it into there. So that's -1, 2, 22, 40, -1, 2, 22, 40, and then this is actually cubed. Sorry, I'm trying to hold this all in my head. It's -40. Boom. And again, when we plug in this for our x, we get 3 plus squared plus -40. We get -$91.67. It's pretty bad. And then when we change it to 3.45, we get $88.87. Still not great, to be honest. So this is our final answer. These are the x and y coordinates of the minimum and maximum. Psych! We need to figure out which one's a minimum, which one's a maximum. It's pretty clear that this one can't be the maximum because it's smaller than a different number. And this one can't be the minimum because it's bigger than another number. So this is our minimum. And this is our maximum. The other way we could have done this is we could have said, when we graph this, oh shoot. When we graph this, our minimum is here, our maximum is here. Our function looks something like this. So we could have seen that this needs to be the minimum and this needs to be the maximum, just by where the function looks like. Okay, y'all. I said that we would add to the notes during this video, but I think I don't want to do that. So instead, we're gonna think about that on Friday. That's all we got. Come to office hours if you have questions. Email me if you have questions. Other than that, I will see you on Friday.